Hello, everyone, and welcome to our ADMET Predictor webinar. My name is David Miller, the Director of Cheminformatics at Simulations Plus.
And I'm Mike Lawless, Senior Principal Scientist.
Today we'll be discussing how to improve your compound design and screening using ADMET property prediction and PK simulations. This is the second webinar in a two-part webinar. Yesterday's webinar focused on medicinal chemistry tools, and today's webinar will emphasize DMPK tools. An opportunity to ask questions will follow the presentation. Please enter your question by using the questions pane on your GoToWebinar control panel. This webinar is being recorded for playback at our website, www.simulations-plus.com. You can also contact our distributor in your country. And with that, I'm going to hand it over to Michael Lawless.
Thank you, David, and thank you, everyone, and welcome to the webinar. We really appreciate you taking the time out to listen to what we have to say. This next slide is simply an outline of the talk. So first, I'm going to discuss ADMET property prediction. This will include properties from our physicochemical and biopharmaceutical metabolism and the new transporters module in ADMET Predictor X, which we expect to release at the end of next month or near the end of next month. Then I'll discuss the ADMET modeler module. This is the module that we build all the models for these various modules. And we typically use artificial neural network ensemble models. And we can create classification or regression models, and each one of those have confidence and uncertainty estimates in them. And then I'll demonstrate building different models in the ADMET modeler module. In the final section, I'll discuss the HTPK simulation module. So this stands for high throughput pharmacokinetic simulations. With that, you can calculate fraction absorbed and oral bioavailability. And then we've added some new columns in APX. So I'll discuss those new columns and the equations that go with them. And then finally, I'll discuss estimating the dose required to reach a total plasma concentration. So in this model, you're kind of putting all of our models together and incorporating them into a PBPK model. This next slide discusses what's happening in vivo. And all the tools in ADMET Predictor are there to generate ADMET properties, which you can use in PK simulations, and to kind of tailor your molecules for getting high oral bioavailability and staying in the system as long as possible in order to get the maximum therapeutic benefit. So in this example, we're dosing the compound orally, and it would go into the stomach where it would dissolve and start dissolution. In the stomach, the pH is about between 1 and 2 in the fed state, or excuse me, in the fasted state. And so the pKa of the compound is very important and has a very important relationship with the solubility and therefore the dissolution of the compound. Aqueous solubility is also incredibly important. And with our models, we can not only predict the aqueous solubility, or what we call the native solubility of the compound, but we can also predict the pH-dependent solubility. So that kind of combines the pKa of the compound and the aqueous solubility. Biorelevant solubility is the solubility in simulated gastric intestinal fluids, and that's really the media that is in the gut, but that's highly related to the aqueous solubility also. So as the molecule works its way down the GI tract, so most of the dissolution can go into the stomach, then it starts working its way down the GI tract. Only the part of the compound that's in solution can be absorbed into the gut wall. And once it enters the enterocytes, that's in turn the fraction absorbed. Jejunal permeability is very important. The higher the permeability, the more it's able to cross this barrier and enter into the gut wall. Transcellular permeability is also taken into account in our HTPK module and in GastroPlus, which is our PBPK modeling package. So this is where compounds, instead of going through a cell, they would go in between the cells, and this is available for small molecules. Log D versus pH is very important because the distribution coefficient is highly related to the permeability and how much would get into the gut wall. Once the compound entered the gut wall, it's moved into the portal vein, which then transfers the compound into the liver where it is metabolized. So models like our human liver microsomal clearance, and in the next version, hepatocyte clearance are very important here, along with hepatic uptake. So this would be important for compounds that are transported into the liver. And we'll talk about this when we discuss the new transporters module in ADMET Predictor. Once the compound clears the liver, gets on the other side of the liver, it enters systemic circulation. And here it starts mixing with blood. So you look at plasma protein binding, blood to plasma ratio, concentration ratio, and volume of distribution, which all affect the clearance of the molecule also, along with the metabolism in the liver. And so once it gets on the other side of the liver, that's the oral bioavailability, or the fraction including first pass metabolism. And then in this inset here, I just show CP time curve, so the concentration in the plasma at 3 different doses of a compound. This next slide shows the modules in ADMET Predictor X. We have 2 new modules, the Artificial Intelligence Drug Design module and the Transporters module. David talked about AIDD yesterday. I'll also discuss the Transporters module today. These 4 modules are mostly artificial neural network ensemble models. So we have Physicochemical and Biopharmaceutical module, metabolism, toxicity, and the transporters. These are mostly whole molecule properties such as log P, log D. With metabolism, we're looking at metabolizing specific atoms in the molecule. So some of these are atomic-based models. Then we have toxicity and transporters. The HTPK simulation module I kind of introduced on the previous slide. ADMET Modeler is what we use to build all of these models, and I'll go through a demonstration of that program or that module. And then MedChem Studio was discussed last night, and these are tools for medicinal chemists to analyze SAR and create new molecules. This next slide shows the models in the PCB module. Incidentally, all of these modules can be purchased separately. So you can purchase just a single module to run the program, or you can purchase all 8 modules. For this next version of ADMET Predictor, we've taken the transporter models that were previously in the PCB module, and we've moved them to the transporter module. So I've taken those out of those slides, these slides. The first model we have at the top is the multi-product ionization constants model, or PKA model. This model was enhanced within the last several years with data from Biopharmaceuticals, who gave us the structures of their compounds along with the experimental PKA, and we incorporated that into our already very nice model to enhance that model and really bring the root mean square error down for that model. And this is one of the best models out there. We've entered contests and typically finished first. The program is written very efficiently where it can calculate these PKA constants very quickly. And you'll see this in some of the demonstrations. So this is the basis of a large number of models. Next, we have the log P model, which is the octanol to water partition coefficient. So this is just an arbitrary, or whatever ionizable groups are in the compound, that's the pH. So the pH isn't controlled in this experiment, whereas in the log D experiment, that's at a specific pH. So this model takes and uses the log P model kind of as a basis, along with the multi-product ionization constants. And then there's another fraction that some coefficients in the equation are calculated. So this model is dependent upon pH, and we can create a log D versus pH plot. Next, I'll move over to the solubility models. I already mentioned the aqueous solubility model. This can be, again, combined with the PKA model to predict the solubility at a certain pH. And I'll show an example of that and illustrate how ionization affects solubility and that further affects fraction absorbed. Then we have models for fasted and fed simulated intestine and gastral fluids. These models were built when we outsourced a lab at the University of in the US here, and they performed experiments on about 300 compounds that we specified, and then we used those results to build these models. We also have some pharmacokinetic models, such as the major clearance mechanism, which is known as the extended clearance classification system. This came out of a publication by Pfizer that looks at molecular weight, whether the molecule is neutral, acidic, basic, or Zwitterion, and it also looks at the permeability to classify the molecules into 6 classes. And in the end, they're trying to predict if it's cleared, if the major clearance pathway is via renal uptake, or excuse me, renal, hepatic uptake, or metabolism. We also have models to predict plasma protein binding in both rat and human, and blood to plasma ratio in rat and human. We have a QSAR model that will predict the volume of distribution. We also predict the fraction unbound liver microsomes. And then we have several models based on this extended clearance classification system that just predict. One of them is a ternary model that predicts if it's renal, hepatic uptake, or metabolism. And then for permeability, one of the most important models is the human jejunal permeability, or PEF model. And this is highly related to the fraction absorbed, and with that and the solubility are major determinants of the fraction absorbed of a compound. Okay, so let's get into a demonstration just to demonstrate the effect of ionization on solubility. So here I've opened up ADMET Predictor X, and so if you go to the help menu and view about, this is version 10.005. So this is an internal version that hasn't been released yet, but it's in very good shape, and we're currently working on the documentation, and we expect to release this at the end of August. So in this slide, I'm just showing 3 compounds. These are all aminoquinazolines, so an amino group and a quinazolin. These were some of the first, this was the first scaffold of kinase inhibitors, and they were very active in kinases. These, I think EGFRs were the first kinases that they targeted, but they did have solubility issues. So example, this molecule, you can see is fairly hydrophobic, and the crystal packing forces would make it somewhat insoluble. So under here, we have a tool called the BCS Explorer. And the BCS Explorer will classify the systems into one of the 4 BCS classes. And this is based on permeability. And so here we're using our PEF model, and we have a cutoff of 0.5. So anything below 0.5 would be classified as low permeability. Anything above that value would be classified as high permeability. And then on the y-axis, we have the dose divided by the solubility. So the solubility is in the denominator, and so the higher the solubility, the lower the number. So these are the high soluble compounds on this side. These are the low soluble compounds on this side. So for these 3 molecules, we have 3 different doses, 5, 50, and 500 milligram, and we can label the doses along with the molecules here. And they all fall into BCS class 2. So these are high permeability, low solubility compounds. And with class 2, what happens is that the compound dissolves a little bit, and then it's quickly permeates into the gut wall, and therefore more of the compound can dissolve. And so this is kind of a sink effect, and it allows some of these compounds to get very high permeability, or excuse me, a high fraction absorbed. And we'll illustrate that in some of these plots here. So if we look at this first molecule and we calculate the PK microstates of the compound, so There are three protonatable amines in this, so the exocyclic nitrogen and the two-ring nitrogens. And so at the very lowest pH, all of them are protonated, or all of them have a hydrogen attached. As we increase the pH, one of the protons is going to fall off. And for this particular molecule, this nitrogen here is the least basic and falls off the most. And we predict that about 83% of the species would be represented by this microstate here. As we further increase the pH, another hydrogen falls off, and falls off the exocyclic nitrogen and nitrogen 3 of the quinazoline ring. So N1 would be protonated below 3.83, and then above 3.83, we're predicting the compound to be neutral. And we can show all of these states in a graph shown here on the right. This is the fraction ionized versus pH, and we have a line in this plot for each one of these, excuse me, 6 microstates. And so you see here at high pH, biological pH 7.4, we can double click on this graph, and up will come a text window with the fraction ionized at the specific pH. So at pH 7.18, most of the molecule, all of the molecule is in the neutral state. We can also show the macro states. And if we look at pH about 1.5 here, most of the molecule now is in the +1 state. So it would be in the state where this nitrogen is protonated. And protonation increases the solubility. It decreases the log D, but it increases solubility. So when this is in the stomach, it has a better chance of dissolving at that particular pH. So we can take a look at the pH, or the solubility versus pH plot, which is shown in the S plus S pH right here in this column here. So this is what we call the native solubility S plus SW model. So this is just the compound without buffers in it. And then we can predict the solubility at pH. Now this is the default is 7.4. And we can change that when we calculate ADMET properties. So you have a pH window here, you could change that to whatever pH you want, and this solubility would be reflected in that particular pH. We can double click on this cell to bring up another window which will display the solubility versus pH profile for this compound. So once it reaches the stomach, with a pH below 1.5, the solubility starts to increase somewhat for this compound. So if we were to take this compound and perform and then analyze what it would look like in the stomach. So this is a plot of the pH versus the various compartments in the stomach and along the GI tract. So in the stomach, the pH is a little over 1, say 1.3. And then when it reaches the duodenum, it goes up to 6, and then steadily increases until ileum 3, and then it decreases a little, and as it gets into the ascendant colon. And then this red line here represents the transit time. So a compound will typically spend about 15 minutes in the stomach, another 15 in the duodenum, a little bit longer in the jejunum, and then slowly decrease in time to ileum 3, and then ramps up highly in the cecum and even further in the ascending colon. So for this molecule, it would mostly dissolve here, and then when it reaches this, it would the solubility would be lowered because it wouldn't have as many ionizable groups. So if we look at a simulation in Gastro Plus for this compound, here we're plotting the mass versus the amount dissolved versus the simulation time. So this is for a 100 milligram dose, and in the first 15 minutes while it's in the stomach, a lot of it dissolves, but the solubility at pH, this is the predicted solubility at pH 1.3, is 0.46, and this is less than the concentration of a 100 milligram dose in the stomach. So the whole dose is not dissolved, and we estimate almost 50% or 50 milligrams of it dissolves in the stomach. And then as it works its way down the GI tract, the rest of it starts to dissolve, but it still only gets up to about 65, 66 milligrams that are dissolved, and the rest would be cleared in the feces or excreted into the feces. And so we predict the simulation shows a fraction absorbed of about 68% for the molecule. Now let's take a look at a similar molecule, but here we've added this morpholine ring as a side chain on to the quinazoline ring. So again, we can take a look at the pKa profile and graph it. And here you see, that the neutral state starts to fade out around pH 7.4. So this is the pKa, the first protonatable group. So it exists as kind of half singly ionized and partially ionized. And then when we get down into lower pH and GI, the percent or the fraction ionized is 99% in the +2 state. And so this has contributions both from the N1 nitrogen of the quinazoline ring, and also the morpholine ring is protonated here. So now we've got two groups that are protonated at low pH. And what happens here with the solubility versus pH plot is that it goes up sharply at these low pHs, and therefore it's more soluble. So let's just take a look at this and let's calculate the solubility at pH 1.4 and then, or 1.5, and then just kind of compare these compounds here. So again, if we go into the Physicochemical tab, so here we see that this is over an order of magnitude higher than this at pH 1.5. And so here's a plot of the two compounds on the same graph, and you can see that this one is much more soluble at the low pHs. And so what happens when we simulate this in GastroPlus is that almost all of the compound is dissolved in the stomach. So it gets over 90% of it, or 90 milligrams is dissolved. And then when it works its way down the GI tract where the pH increases, then it crashes out or recrystallizes in the duodenum, and then slowly dissolves to get a fraction absorbed of over 100, almost 100% over the 24-hour time period. But most of it's dissolved, or almost all of it's dissolved within the first 8 hours. Okay, now let's move on and discuss the metabolism module. So we have a large number of models here. These on this side are all related to recombinant CYPs. So we're looking at specific isoforms of cytochrome P450, and we have several models, 9 different isoforms, where we predict whether the compound is a substrate or a non-substrate for a specific CYP isoform. We also have models to predict sites of metabolism for these 9 isoforms, and then we also have models to predict Km, Vmax, and clearance for the 5 major CYP metabolizing enzymes. We have models to predict liver microsomal clearance. So this is HLM and RLM clearance for both human and rat. We predict CYP inhibition if the compound is a UGT substrate or non-substrate. And in the last version, we also depict the metabolites for this, and I'll show an example in the demonstration. We also predict aldehyde oxidase, substrate, non-substrate sites of metabolism, metabolites, similar to this suite of models for cytochrome P450, and then esterase metabolites. So our recombinant CYP models are kind of a tiered approach. So the first thing we do is we take a molecule and we predict whether it's a CYP substrate or not. So in this example, we take dilatazine, and we predicted that it is a substrate for 4 out of the 5 major isoforms. So we're predicting that it's not a substrate for 1A2. So we wouldn't consider any 1A2 metabolism going forward for this compound. Then we predict the sites of metabolism. And so this is just illustrated for 3A4, but we'd also have similar pictures for the other three recombinant CYPs, of which this is the substrate. And we use ADMET Modeler again, but this time these are based on atomic properties. So we calculate a score for each one of the atoms in the molecule. The higher the score, the higher the propensity for metabolism. And then we have kind of an algorithm that says, okay, which of these are we going to identify as sites of metabolism? So these would be the highest scoring atoms in the molecule. Once we've identified those, then we also predict the clearance, Km and Vmax for each one of the atoms that are sites of metabolism and also a substrate. And so again, we would have predictions for the other three isoforms. And then finally, putting this all together, we would, you can take the structure and then generate the sites of metabolism, and then we depict the metabolite. So for example, in this molecule, we're predicting that the sulfur gets oxidized. We're predicting that this nitrogen gets demethylated. So what happens is that this carbon gets hydroxylated, that forms an unstable intermediate, which would fall apart into the secondary amine. Similarly, the methoxy group gets demethylated by hydroxylating this position and forms an unstable intermediate, which would fall apart into the phenolic compound. So let's take a look at some of our models within the metabolism module for these particular molecules. So the first thing we can look at is the CYP substrate and non-substrate models. And in this display, we're looking at a wedge plot or a star plot. So this shows all the recombinant CYPs. And if the wedge goes all the way to the end, that means that it's a substrate, okay? So for this compound, we're predicting 5 of the isoforms. This would be a substrate for 5 of the 9 isoforms. This would be a substrate for 3 of them. And finally, this would be a substrate for only 2 of them. We can show the sites by double-clicking on the cell for the site, and it will put up a display similar to what I showed in the graph. If we double-click on a structure image, it will bring up the molecule in ADMET, in MedChem Designer, and we can click on the metabolite button, and this will generate the metabolism tree for this compound. So we get hydroxylation here, the N oxide produced here, hydroxylation over here. Aldehyde oxidase is going to put a hydroxyl group here, which would rearrange into the keto form here. And then finally, this other group is hydroxylated. So these are the 5 major isoforms of cytochrome P450. If you wanted to include the other 4, you would just highlight these tabs or turn these buttons on. We can also predict UGT metabolism. So this combines our models of UGT substrate, non-substrate. So it's predicted to be a substrate for 1A1, 1A9, 1A10, 2B7, and 1A4. And we recently added this in ADMET Predictor 9.5. It kind of analyzes the groups in the molecule and tries to produce the metabolite. So for this, these 4 UGTs, it's predicting mostly that they would glucuronidate the nitrogens in the ring, whereas 1A4 preferentially glucuronidates a non-ring nitrogen. We also in 9.5 introduced esterase metabolism, and this was done by looking at prodrugs. Prodrugs are compounds which they try and metabolize a group, and they protect a group, basically, allow it to get into circulation, and then this group would come off, and they would therefore enhance the fraction absorbed and deliver that to the target. So for esterase, we need to go to this bottom menu. And what happens here, even though this is not an ester, it's a carbamide, it would typically be cleaved here by the esterase. So you would imagine it's similar to if this was a carbon, that this group would come off, and that forms kind of an unstable amide, which would decompose into the amine. Okay, so let's go ahead and close that out and then go back into ADMET Predictor for the final part of this section on ADMET properties. So in 2017, the US FDA put out a guidance for looking at drug-drug interactions for transporter-mediated compounds, and they list several chapters on PGP and BCRP and various other transporters, and determining if the investigational drug is an inhibitor or if it's a substrate of various transporters. The European Medicines Agency also put out a webinar, or excuse me, a guidance. Here they're specifying P-glycoprotein, which is also known as MDR1, OATP1B1, OATP1B3, OCT2, OAT1, OAT3, and BCRP. These are the major transporters that they're interested in. Kind of secondary transporters are OCT1, MATE1, and MATE2. And then they also list inhibition of BSEP as an important transporter. This BSEP is the bile salt excretion export pump. It is there to give homostasis to cholic salts. So the substrate is typically a cholic salt, but investigational drug can be an inhibitor of BSEP, and that mixes up the balance of the taurocholate acids. And our sister company, our DILIsym, is a company under the Simulations Plus umbrella that performs quantitative systems pharmacology and toxicology. And so when they have a tool called DILIsym, which looks at drug-induced liver injury, and one of the experimental things they have to measure is BSEP inhibition and get the IC50 for the compound. And then they plug that into the model along with the inhibition of other transporters and build a predictive model to predict liver injury. So DDIs most of the transporters of DDI interest are expressed at the epithelial layer of intestinal enterocytes, hepatocytes, and kidney proximal tubes. So in this diagram, we're showing where the transporters are located and whether they're efflux or influx transporters. So first we start in the intestinal epithelial. We have the lumen on this side and then the blood here. And so a compound that is a PGP or BCR P substrate would be efflux back into the lumen. And if you would inhibit this, you would allow the compound to go through here. For hepatocytes, we're looking at OATP1B1 and OATP1B3. Here, the compound is in systemic circulation, and the transporter would pump it into the liver, and it would be metabolized in the liver. For kidney proximal tubes, we have OATP1 or OAT1, OAT3, and OCT2. So these are for anionic compounds, these are for cationic compounds, and these are transported into the kidney where they would be cleared in the urine. Then on this next slide, we show examples of the perpetrator and the victim. So digoxin is a PGP substrate. So if you would co-dose that with quinidine, which is a PGP inhibitor, you would increase the exposure of digoxin. And here it shows that would increase by 1.7-fold. Rifampin is a PGP inducer. So this is going to create more PGP, which would create more efflux transporters, and would prevent digoxin from entering into crossing into the blood. And so this would lower the exposure of digoxin. So in this case, you might not be getting enough of that compound to reach a therapeutic level. And so this would obviously be bad for the disease state, whereas this one could potentially lead to toxic effects. And then finally, dronedarone is a PGP inhibitor. So this would let more digoxin go through the system, and it increases the exposure by 2.6-fold, again, potentially generating a toxic effect. So these are the transporters we're going to have in our new ADMET Predictor 10 program or release. And what we're going to do is we've moved these models that were in 9.5 out of the PCB module into a transporters module. And we're going to give away that module for the first year. So that'll be free if you have the PCB module. And this will include OAT, these 6 models up here. These are for KM. So this is a regression model that predicts quantitatively the KM. And then the substrate inhibitor models are classification models. So these would indicate if the compound is a PGP substrate or not, or a BCRP substrate. We rebuilt this model for ADMET Predictor 10, including more data. This was already in 9.5, so we're keeping the model there. And then these are all new models here. Then for an inhibitor, we rebuilt the PGP inhibitor model. And we also rebuilt the OATP1B1 model with additional data. We kept the 9.5 OCT2 inhibitor and BCEP inhibitor models, and then built 5 new models by recovering the data. So for these inhibitor models, what we did is a lot of the data is, say, percent inhibition. So they test the compound at a fixed concentration and a fixed concentration of the substrate. We took those that data and we converted it first to an IC50, and then converted the IC50 to a KI using the KM, the substrate, and then had a cutoff of probably 20 micromolar. If the compound had a KI below 20 micromolar, we tagged it as an inhibitor. If it was above that, it was a non-inhibitor. And then we've also built a BCEP IC50 model, and this was helpful for our colleagues at DILIsym. So these are just examples of the KM models. These are all regression models. The data sets are not too small, but some of our other models, such as the log-P model, is much better. So we we culled the literature for all of this data as best we could. These are the substrate, non-substrate models. So we have both the training and test sets listed here for each individual model, the number of negatives and positives, the total, the number of correct, and then concordance, sensitivity, and specificity. And you see that all of the values are above 80% for all of the models here. Similarly, for the inhibitors, we get very good statistics for all of the models, and so you can have confidence in our predictions there. Okay, now let's move on to ADMET Modeler, which is the model building module of ADMET Predictor. So as I mentioned earlier, this is what we use to build all of our models. So what does the QSAR technology represent? So in the end, what we want to do is take an arbitrary molecule, plug it into a QSAR equation, and predict properties such as log P, PK, et cetera, listed over here. And so our starting point for that is data. So we need experimental data on the particular endpoint. And the more data, the better, but we need to curate that data and make sure it's good data. And then we would take all of the molecules and we would generate descriptors. So these descriptors, we calculate 2D descriptors from just the 2D information of the molecule. So we might have descriptors that would be the count of oxygen atoms or the count of nitrogens or the count of phenyl rings, etc. Then we have other descriptors that are based on semi-empirical quantum mechanical calculations. We have ones that kind of look at the environment of the compound, etc. Then these descriptors are used in training algorithms, and the training algorithms try and relate the descriptor values to the endpoint. And so they create a mathematical model to predict these. And once you have the mathematical model, then you can plug in an arbitrary compound and predict an output. So that's kind of the overview of QSAR modeling. This next slide lists some of the keys to creating good models. And the most important thing is curating your data. If your data set has garbage in, you're going to get garbage out. And especially with these newer algorithms that tend to overtrain the model. So they learn the errors in the data and try and can accurately predict the errors. And so if you have errors in your training data, the newer models are going to memorize that or use that information. And then when you try and predict an arbitrary compound, you typically get an incorrect answer or higher RMSEs than you do in your training set. We deal with a lot of data. Our data sets come from various sources. One of them is just literature. So one thing we have to do is rectify data from one lab to another lab. So if we get two, say, log Ps from two different labs, we would have to determine which one is correct. In some cases, we might take an average. In other cases, we would look at the journal article and maybe throw out that information as a different experiment. Using appropriate and accurate descriptors is very important. For our general whole molecules and the descriptors that are available in ADMET Predictor are typically whole molecule descriptors. For things like our pKa molecule model, our sites of metabolism, these are endpoints where a specific atom in the molecule gets changed. So in a site of metabolism model, it might be hydroxylated. So atomistic descriptors are more important. So we have a whole slew of atom-based descriptors that we use to build the models. Pre-filtering your descriptors. So this entails eliminating descriptors that are highly correlated. Highly correlated descriptors are bad for QSAR models because it can give kind of false root mean square errors, etc. So we pre-filter, and I'll talk a little bit more about that on the next slide. We always validate on an external test set. So we have a training set that the molecules are trained, and we set aside a test set. And then once we build the model, we make predictions on the test set and to validate the model. We use good training algorithms, which we've kind of focused on artificial neural network ensembles. We don't overtrain, so we've got a part of the algorithm avoids, it's called an early stopping algorithm, and it avoids early training. So in our models, you will never see where the training set has perfect statistics and the test set has not so perfect statistics. And then finally, we use wisdom of the crowds. And so we don't use a single artificial neural network. We use 33 artificial neural networks and then either take the average or we do some really nice things with classification models. This next slide just talks through building an artificial neural network ensemble model. So the first thing we start with is structures and experimental data. And we go to great lengths to curate the data, make sure the units are correct, make sure the structures are correct, etc. Then we compute over 300 descriptors, and these are based on constitutional, topological, hydrogen bonding, ionization. The ionization comes from our pKa model. Electrotopological, so these are E-state indices that look at electronegativity of atoms in groups, and then charge and reactivity. So now we have the rows as the molecules, we have one column that is the endpoint or dependent variable, and then we have a large number of columns that are the descriptors. Then we analyze these descriptors. So first we remove low variant descriptors. So let's say your data set has no bromine atoms and you have a descriptor that is the number of bromines. Well, that column is just going to be zeros, and we would throw that out because you're not going to be able to predict the difference in the biological activity with a column of zeros. Next, we would compare every column to every other column in the spreadsheet and calculate its correlation coefficient. And if it's above a user-specified cutoff, we would drop one of those two columns so that we end up with no correlated descriptors in the final set. Next thing we do is create a test set, and then we sequester it and set it aside, and there's several methods for creating the test set. Then we would take the training set and we would train the algorithm. Now, a priori, we don't know how many neurons and descriptors are going to create the best model, so we create several models with different architectures, i.e. different number of neurons and descriptors. And to identify which descriptors are going to create the best model, so if we have 200 potential descriptors, but we only want to use 10 of them in a model, we use something called sensitivity analysis, which selects the best descriptors to create a model. Then we create the training set or train the model, and then we apply it to the test set and then represent the statistics in a grid. So the grid, each cell will be a different artificial neural network ensemble or architecture, and then we analyze those statistics and select the best model. And the best model is an ensemble of 33 artificial neural networks. In this cartoon, the triangles are the descriptors in the model. They are multiplied times a coefficient represented by this line and summed in a blue circle, which is the neuron. So in this example, there are 4 neurons, so this would be a 4-neuron model. Each one of the neuron is multiplied by a coefficient and summed in the output. So this is the prediction of the model. And all of these coefficients are optimized within the, when we train the models. And they're initially assigned random values, and the algorithm optimizes those coefficients to minimize the error between the predicted value and the observed value. And because these are randomly generated initially, they can go to different endpoints, and that's why we can use 33, or we can create 33 ensembles to give the best model, because they're all slightly different, because they all have slightly different starting points. This next slide shows just examples of 2 types of models, classification model and a regression model. So with the classification model, you're simply classifying the molecules as no or yes. So this may be toxic or non-toxic, it may be substrate or non-substrate. And we create what's called a truth table. So in the truth table, we've got the observed values in this plot on the y-axis and the predicted values on the x-axis. In this quadrant are the true negatives and true positives. In these quadrants are the false negatives and false positives. So these are the predictions we get correct. These are the ones we get incorrect. And then for every one of our models in the user manual, we present a table like this, giving the number of training and test set molecules, the number of correct, and then the concordance, which is the overall accuracy, how well we did overall in the predictions, the sensitivity, which looks at how well we predicted the observed positives. So it's the number of true positives divided by the sum of the false negatives and true positives. So the total number of observed positives. For the specificity, it is the number of true negatives divided by all the observed negatives. And we pay particular attention to this. Typically, we want all our statistics above 80% for concordance, specificity, and sensitivity. And the reason is a lot of our data sets are highly skewed. So we may have 90% of the compounds be a negative and 10% be a positive. In this case, you could predict everything to be a negative and you'd be correct 90% of the time, which is very good. I'd like to be correct 90% of the time. but you'd have 0 for the sensitivity because you didn't predict anything to be a positive. And so there's no way you can get any true positives. And so that's not a very useful model. Then for the regression model, here we're plotting the observed value versus the predicted value, and we're just trying to get as close to the line of unity. And you can see this is our log P model. We train on 11,332 molecules, and we test on 1,253. And so this is a very large data set, and we get very good statistics. A root mean square error of 0.3, so that's very good for the kind of the span on average of this model. We also flag applicability domains. So the way we calculate the applicability domain is we take the training set, and for each one of the descriptors in the model, we know the minimum and maximum value, and then we kind of add a little 10% around the edges here. Then when you predict an arbitrary molecule, if all of the descriptors are inside this bounding box, then we would say that is an in-scope model. So all the things in blue and black are in scope. If any one of the descriptors is out of scope or above the minimum or maximum value, then we flag it as out of scope, we color it in magenta, and we underline that prediction. And depending on which descriptor is out of scope, that data or that prediction is trustworthy or non-trustworthy. So you kind of have to get into the guts to look at that a little bit more efficiently. For our classification models, we also include predictive uncertainty. So for each prediction in the classification, in parentheses, we'll put a value of the percent confidence we have in that prediction. And that's based on analyzing the predictions in the training set. We typically recommend that predictions with a confidence estimate of below 60% are kind of undecided because the model is not really sure of its class. We also create regression uncertainty. So in this case, we show the error bars. Again, this is by analyzing the spread of predictions for the 33 artificial neural networks in the model. And the higher the spread, the higher the uncertainty, essentially. And so we'll show that also. So let's go into ADMET Predictor and create a classification model. So here I've entered data for 321 molecules. These are from some publications, and they experimentally measured the hepatocyte clearance at 1 micromolar. So this column is the clearance. And since it's hepatocytes, some of the molecules bind to the hepatocytes. So you need to correct the hepatic clearance for binding to the hepatocytes. And then we also take the log of the value. So these clearances range from 0.3 microliter per minute per million cells to 445. So these are cleared very fast in there. And since that's a very large range, then we take the log of that. And so you can see that it varies from negative 0.45 to 3. So that's over 3 orders of magnitude range in the data. Typically for a QSAR model, you want at least 3 orders of magnitude for a range on a regression model. Then I've also added this column that is, we're going to create a binary classification. So what we've done is just segment this data. And this is just an example. And we've kind of just generated about 50% of the molecules to be low clearance or to be no for this high clearance column. And then 50% of the molecules, the other 50% is high clearance. So that's where we set our cutoff on this for this. So the first thing we need to do is calculate descriptors. So we click on the ADMET icon here, that calculates the descriptors. And then if we hit this tab, we can see some of the descriptors. And the first descriptors are these things like counts of heavy atoms, counts of carbons, etc. We go down further. These are the E-state indices for specific groups. These are kind of shape indices, etc. Then when we want to create a model, we click on this icon to bring up a dialog box that asks us to specify the dependent variable. So this is what we're trying to predict. We're going to do the binary classification molecule on this high clearance, and then click OK, which will bring up the first dialog box in ADMET Modeler. So we've selected the dependent variable, and these are all the descriptors that are available. And the first thing it does is kind of filter out the ones that are this, have low variance in there. I'm going to add a log P descriptor. Some modelers, don't like that. They would say that you're building a model on a model, but I typically include log P because people understand how to what log P is and how to modify it. Then I click next. So this is a wizard working our way through. Here's where we would specify the test set. The default is Cahonin map, which is a good method for calculating the test set. What it allows you to do is generate all of the span of the chemistry space in the training set, or in the data set would be represented. But the negative is that the test set compounds are very similar to a molecule in the training set. Another method that I'm going to specify here is stratified sampling. With this, it partitions the data set and then picks a certain random number of compounds from each bin. And I'm going to use this method. I'm going to specify 15% of the molecules in the test set. Typically, our models have 10 to 20% of the molecules in the test set. So then I'll click OK, and then specify the sensitivity method. The default is truncated linear analysis, which is the fastest method. I'm going to use one called input gradient, and this is a nice method because it balances speed with accuracy. With the input gradient method, we can multi-thread the calculations, so that increases the speed, and it's fairly accurate. So I'll select that one, then I'll click next. Here's where we're specifying our grid. We can click autofill, and it kind of gives a first estimate of the grid. And typically I change this, and what we typically do is kind of start out with a coarse grid and then we refine it. So I'm going to create models that vary from 1 to 7 neurons with a step of 2. So it's going to create a 1 neuron model, a 3 neuron model, a 5 neuron model, and a 7 neuron models. Then for the number of inputs, we're going to vary it from 20 to about 60 inputs. Typically, I don't like this number to be larger than 20% of the overall data set. So here we have 320 molecules in it approximately. So 20% of that would be about 64. I'm going to set it at 65. And then I also set the number of Monte Carlo tries for starting points. So this is kind of the initial seed that I talked about earlier. I click summary and then build, and it prompts me for the name of the project. So the project will be, the program will store all the data files in the folder, and this will be the name of the folder. So I click OK. Now it wants to know which class represents the negative class. And it does this because, to get the sensitivity and the specificity correct for the classes. It doesn't know arbitrarily what that's going to work. And so here, kind of messed up. I meant to do a step of 5 here. So let me correct that. Let me go ahead and stop this and go back into the model settings. Sorry about that. So I want to do a step of 5 here, and then go to summary and build, and then build a new model here. Okay, so now it's starting to build models here, and we could look at the log file while those are building. So the log file is going to contain all the information for the setup, what descriptors are thrown out. So these are the underrepresented descriptors. These are highly correlated descriptors. So it's going to throw out one of these 2 descriptors. As we go down further, it also performs multi-correlation to try and further remove some of the correlated descriptors. and then finally comes up with a set of descriptors it can choose from, and then uses the algorithm input gradient to select the initial or the descriptors to go in the 20 input 1 neuron model. And you can see it's selected log P here as a descriptor. Once it's finished, it selects, it uses an algorithm to select the best model. Here it's selected this 5 neuron 30 input model. So we could take a look at the statistics here. And typically what we would do is iterate over and over again, look at the statistics, and then finally choose the best model after getting a very refined grid. And what we can do is export this model. So I'm just going to call this clearance class model. We would typically set a tooltip. So this would be information on the units or maybe the cutoff for this particular model, and then save it. We can also save the project if we want to look at it later. So I'll save this on a desktop, and it's going to create this folder in here, and then all the files will be under that. And if at a later time, I can open that project and reanalyze the data, or I can build more models. Now, when I exit out of ADMET Modeler and go back into ADMET Predictor, it knows that we've added a new model. So it asks if we want to recalculate the properties. I click on yes, and then it calculates them. And if I go into my user models tab, we would see the new model that I created here with the predictions. And it would also have the values of the uncertainty in parentheses here. And I just want to show for a regression model such as log P, in this version, we're showing the range of values. So this is 1 sigma deviation away from the predicted value. So 2.74, the uncertainty gives a range from 2.4 to 3.05, excuse me. And it would be just a bell-shaped curve centered around this, because this is built in linear space. Okay, so now let's move on to the final section, which is our HTPK simulation module. And this is can be used in discovery for virtual compounds or compounds you're trying to predict as lead compounds in order to predict the PK properties of the molecule. So with our HTPK simulation module, it predicts for an immediate release tablet. So this is the only dose form we have currently in either a rat or human species. We predict the percent absorbed or the fraction absorbed, also known as the human intestinal absorption. We predict oral bioavailability. This can be termed F% or percent FB. Then another tool is the dose required to reach a specific user or user specified total plasma concentration. So here you could, for example, use IC50 values. So you've tested your compounds and obtained an IC50 value for them, and you would want the total plasma clearance to be above the IC50 value in order for it to be an efficacious compound. And we can predict the dose that would be required to reach that plasma concentration. We also have a prediction of the mechanistic volume of distribution. So this uses KP models for different tissues and uses an equation to come up with the volume of distribution for a PBPK type model. Now we have similar dose as I described in one of the earlier slides, and we use our Gastro plus ACAP model to simulate the transit along the gut wall, or excuse me, along the GI tract, and I'll show that in the next slide. Now we're creating fairly simple models. So in Gastro Plus, you can specify enzymes in the gut wall that could potentially metabolize the compound. And you can also specify transporters. Here, we're just looking at no clearance in the gut wall, and we're not including active transport. So it's all passive permeability into the gut wall, although we do include the transport between the cells, paracellular transport. Then it goes into metabolism. Here we're only considering linear clearance. Again, in Gastro Plus, you could specify Km and Vmax for various enzymes, and you could model nonlinear clearance due to saturation effects. Then once the molecule goes into systemic circulation, it distributes into the tissues, so we're using the volume of distribution. We also include renal clearance and liver clearance. So this part of it is specifically used for the dose estimation and also to obtain CP time curves for these compounds in this module. This next slide shows our advanced compartmental absorption and transit model, known as the ACAP model. So here we're specifically looking at an immediate release tablet, so we don't have to worry about release of the compound. We're just, everything's either undissolved or the dissolved state. And there's a series of equations that we have to solve. The molecule can go from the undissolved to the dissolved state, and then also work its way down the GI tract. So this is a complicated system of equations that must be solved, and then going into the enterocytes of the gut wall, and then out into systemic circulation. So we, in our model, our PK simulations, we use these 9-compartment, the GI tract. What we're trying to encourage here is to optimize the properties of your molecule in the context of a virtual human or a rat. So instead of simply optimizing log P or ionization, you're putting that together with other parameters because they really do affect each other. So for example, hepatic or systemic clearance not only includes the liver microsome clearance, but it also has to include the fraction unbound to plasma and the RBP ratio, along with the liver blood flow. So with the HTPK simulation, you can simulate these and take all these properties into consideration at the same time. This next slide discusses some of the new functionality in ADMET Predictor 10, or the next version in the HTPK module. We're including new output for the oral bioavailability predictions. So this is the total clearance, and I'll show equations for this on subsequent slides. The half-life of the compound, the hepatic clearance, the hepatic and renal clearance. Here, renal clearance is approximated by FUP times the glomerular filtration ratio. And then new output columns for the dose estimate include the Cmax and Tmax at steady state, the clearance at steady state, the half-life of steady state, and the number of doses needed to reach steady state. We also, you can use this on the command line and then import this into other tools. The number of dose intervals can be specified on the CP time curve. We have new command line options, such as the base name for the output files, the where to save the CP time profiles. So in ADMET Predictor X, when you run on the command line, you can also output CP time curves and then import that data into a graphing program to visualize the CP time curves. We also specify, you can also specify a local HIA file. So these are for the parameter files. They'd be similar to the PBPK files in Gastro Plus. So these would specify the physiology of the subject, and then the ACAP model would specify the volumes of the GI tract, et cetera. And so you can specify those to create your own customized version. So some of the new columns in the FB prediction, one of them is the clearance. So here we're using kind of the classical pharmacokinetic calculation here, where we take the dose times the oral bioavailability, here represented by F, and divide it by the area under the curve. So the dose multiplied by the fraction bioavailability. So this is for orally bioavailable. This is just the equation if it's an IV administered one. which we're not simulating in the HTPK module. So an example here is a 10 milligram dose with an oral bioavailability of 0.67 and area under the curve. So you just have to take care of some units here, unit conversion, liters to milliliters, nanograms to milligrams, and then output liters per hour. For the half-life calculation, it's the volume of distribution divided by the clearance. Again, the volume of distribution is typically in liters per kilogram, and we're simulating a 70 kilogram subject. So we have to multiply that by 70, and then the output is in hours for the half-life. The hepatic clearance is approximated by the well-stirred model. So the unbound clearance divided by this denominator, we have the ratio of blood to plasma and the liver blood flow, and then also the fraction unbound to plasma. So when this value here is the HLM, it can be the hepatocyte clearance, you can use experimental values, but we have to convert this to kind of an in vivo units, liters per hour. So we need to know how many milligrams of microsomal protein are in 1 gram of liver, and then how many grams of liver are in the subject. And then some of these are other just converting units, and then ended up in liters per hour. And then once we have this value, we can plug it into the well-stirred model in liters per hour. The liver blood flow is 90 liters per hour. In this example, the RBP is 0.75 and gives you 22 for the hepatic clearance. In the previous version, the way we calculated steady state is by looking at the average of the Cmax and Cmin, and when that kind of reached an asymptote, we would say it reached steady state. In APX, steady state is reached when the area under the curve for a single dose is equal to the area under the curve at steady state. And so this project or dose estimation really uses a lot of estimates in it, and I'll talk more about that when I demo it. But if you simply do a single dose, you can predict the area under the curve out to infinity. So that's represented by this, and that would go out for long term. And this blue would be the area. And then when this area equals the area, simply by looking at just this time frame under the curve, then the compound is said to have reached steady state. So let's take a look now at ADMET Predictor and discuss some of the predictions we can make with this. So here I've read in a set of 671 compounds, and I've got experimental human hepatocyte clearance for each one of these molecules in these columns. Some of these are less than a certain value, so these would be ones that are very highly stable compounds, and then we also have some that are very unstable. Well, some aren't too unstable, but we list those with greater than, and these were all obtained from the literature. Okay, so let's just quickly calculate fraction absorbed for all these molecules. So we simply click on this icon. We're going to calculate it for all of the molecules in here. And I'm just going to use simulate a 1 milligram dose in human. You can specify rat here. I'm going to calculate percent absorbed and oral bioavailability. These columns will have a prefix because you can do multiple doses here using the semicolon delimiter to specify the different values. You could also have another column that is the dose for each one of the individual molecules in the data set. So you could click here and specify that column. You can also specify whether it's liver microsomal clearance or hepatocyte clearance, and then these units would change over here. For the preferred value for the liver microsomal clearance, we're using our model. Again, you could, if you had a column of experimental values, you could input that. And that's what's very important of this particular module. So you can just calculate the in silico predicted values. Then as you synthesize the compound and start getting more ADMET properties calculated for it, you can use those in the simulation. So you can use experimental values in the simulations. This advanced tab will show other properties that you can input. And so we use all of our models here for these, but if you had a column with log P, you could specify it here. Similarly for the aqueous water solubility or the PEF or the fraction bound to plasma. Now here we want these values as percent rather than fraction. And then the default for the volume of distribution is to use the QSAR model. You could also use the mechanistic model if you wanted to. So then all we would do is click run. In ADMET Predictor 10, this is parallelized. So we're doing each one of these PK simulations for 671 molecules, and it just takes a few seconds to calculate all those values. So this is all stored under the simulation tab here. So we have the fraction absorbed, the oral bioavailability, the Cmax, Tmax, area under the curve, clearance. So this is calculated from the equation I showed you, whereas this is using the well-stirred model and then also includes the renal clearance. So these two values, the renal plus hepatocyte clearance, don't always agree. So one's from a simulation, one's from just the linear clearance, and then this is the mechanistic volume of distribution. We can highlight a row and click on the CP time curve to produce a CP time curve for this molecule. So we would run that, and you see the curve goes up, comes down. The Cmax is reached at about 1.5 minutes, and it's about almost 50 nanograms per milliliter. So these are these two columns here. We can also sort on those and find some of the molecules that have high first pass metabolism, etc. Okay, so for this set of data, let's go ahead and calculate ADMET properties, and then we're going to look at a plot of how PEF affects the fraction absorbed. Again, in ADMET Predictor X, those ADMET property calculations are parallelized. I've got 7 processors on this computer, so it uses 7 processors, so you get a nice speed up there. I'm going to take this graph and unplug it, and then I'm going to plot the fraction absorbed on the y-axis and the PEF on the x-axis. So I specify that and then hit OK. And so what we see is the higher the PEF, typically the higher the fraction absorbed. Now these compounds down here are probably solubility limited. If we select this compound here, this is a compound with a PEF of 0.53 and kind of a medium fraction absorbed of 0.5 or 57%. We can highlight that row in the spreadsheet and then put up a parameter sensitivity plot. So if I click this button, it's going to vary both the solubility and the permeability and plot how those values, when you vary those, how they would affect fraction absorbed. So the point right in the center is the predicted values, and then the red line represents the increasing the permeability or decreasing the permeability, and similarly for the solubility, the points are in blue. So increasing the permeability of this compound would increase the fraction absorbed quite a bit. Now let's plot the water solubility of the compound versus the absorption. And here I'm going to use this in log units and then apply this. So the higher the solubility, the higher the fraction absorbed. If we look at a point down here at low solubility, this compound only has a fraction absorbed of 5. So again, let's do a quick parameter sensitivity analysis on that compound. And here the permeability stays flat, whereas the solubility, as you increase it, would greatly increase the fraction absorbed of that compound. Okay, so now let's look at the dose estimation of the compound. So that's done by this icon here. Now, typically you would have a column that you would specify the total plasma concentration. And typically, if you're looking at IC50 values, you want to adjust that for the free fraction. So you would divide the IC50 by the fraction unbound to plasma in order to get the concentration needed to be achieved to get a free fraction equal to the IC50. In this example, I'm just going to say, okay, I want all these molecules to have at least plasma concentration of 50 micromolar in the plasma. And it's going to start with an initial guess of 10 milligrams. And it would simulate a 10 milligram dose, and it would uses an analytical method to estimate how long it's going to take to get to reach steady state. And then once it reaches steady state, it's going to see if it's reached this plasma concentration of 50 nanograms. If it hasn't, it would either increase or decrease the dose in order to reach that. And once it gets up to 1,000, a dose of 1,000 milligrams, then it just basically stops. I'm going to use all the default parameters here. And again, this is done in parallel. So it's very fast, but it's doing a lot of work here because it's having to adjust the dose. So it's going to take longer than performing just a single simulation on a molecule. So we'll wait for that to finish here in a few minutes, or a few seconds, excuse me. And then we'll take a look at the columns that are produced here. Okay, so all done. And then we go into the simulation tab. And these are going to be kind of these new columns over here on the right. So we have the optimal dose. So it's predicting that this would need 105 milligram dose. This is the steady state concentration. So this is after it's achieved steady state, and it reaches that at 3.7 hours. Now that's relative to the very last dose. The area under the curve for the that final dose time is 909, the clearance, the half-life, and then the dose. So it's predicting it would take 5 doses this to reach steady state. So again, let's take this compound and create a CP time curve. And so we're going to use 105 milligram dose for this compound, and we're going to dose it for 5 days. And this is new too in ADMET Predictor X, that you can specify subsequent doses of this. So the default is a single dose every day. You can modify the HIA files if you want to go for more days. Similarly, you can use experimental values, etc. So let's go ahead and click run here. And so this is kind of an odd shaped one. It's cleared very fast, so it does reach steady state and very quickly. And we can use this to change the units to micromolar, and you can see where it's reaching this 0.5 micromolar. So this is the average. So it's the area under the curve divided by the time. So it's the average concentration. So let's see if we can find a few more interesting examples. Well, we could sort this by the optimal dose here in descending order and take a look at some of the compounds that don't quite make it up to they reach it even at 1,000 milligram dose. So for example, this compound we can dose at 1,000 milligrams, and let's just look at a 20-day simulation and run this. And once I've changed this to micromolar, it stays at that. And you can see that the maximum here only gets up to about 0.35 or 35 nanomolar when we specified 50 nanomolar. So it doesn't quite reach its potential. And then this compound only needs a very small dose, and that's because it would have a high oral bioavailability and would reach steady state fairly quickly for that compound. And then in the final example, I just want to show how you can use experimental values. So remember, I read in the clearance here. So let's just do a 1 milligram dose, and let's specify hepatocytes. And if you notice, this units, they change from per milligram of microsomal protein to million cells. And then we have a new model in ADMET Predictor 10, which is the human hepatocyte clearance model. Here I'm going to use the experimental values that I read in, and these values are unbound. So that means they haven't been corrected for, or excuse me, they're bound, so they haven't been corrected for microsomal clearance or for binding to the hepatocytes. So again, I would just run this, and you see again the calculations are very quick and allows you to incorporate experimental data, in this case, your human hepatocyte clearance. And with that, I'm going to finish up and just allow a few more minutes for questions. We really appreciate your attendance. And if you need to reach either myself or David Miller, David's email is david@simulations-plus.com. My email address is mlawless@simulations-plus.com. Thanks for attending, and I'll turn it back over to David for concluding remarks and any questions.
Thank you so much, Michael. There were just a couple of questions that came in earlier. I'll direct them to you, Michael. Can you comment on whether there is a Linux version available?
Yes, so the Linux version does not have a GUI, but it's command line only, and it's very popular for people that do kind of or integrate our predictions with, you know, another backend that they would use as a GUI. And you could download the Linux version and the Windows version. I kind of recommend that. The Windows version has the GUI, and so you kind of understand the models. You can show some of the graphical things like the solubility versus pH profiles, etc., that wouldn't be available in Linux. But we're very flexible with our licensing. The network license costs the same as a standalone license, so you could have ADMET Predictor on a Linux computer and on a Windows computer, and then have either one of those defined as the license server. And so you could run the programs on either of those computers, and they would hit the same license server. So we're very flexible, and we do support Linux.
Yeah, I'll only add that we don't typically release the Windows version and Linux version simultaneously. So we're scheduling the Windows release for end of August, maybe 4 to 5 weeks from now. And then typically we would follow up with the Linux release, you know, ideally a couple weeks later, at the most 3 or 4 weeks. One other kind of interesting question: if someone were to have ADMET Modeler, and let's say they have a lot of internal ADME data, you know, some property, let's say solubility. If they built a model of solubility, could that model be used with the HTPK simulation module?
Certainly, yeah. And let's see. So you would just, you know, click here. You know, you would have the model already defined in ADMET Predictor. You would go to the Advanced tab, and then click on this button here, which is the solubility, and specify that column in here, and it would use that predicted calculation. We would run it in milligram per milliliter, is how we would input that into the program in those units.
And then, yeah,
if
you're using the command line version, you would have to, correct me if I'm wrong, but insert that solubility into the SD file that serves as the input to the HTPK. And then I think there's a parameter file where you would indicate that you were preferring to use your own internal solubility model instead of the default ADMET Predictor solubility model.
Exactly. Yep. Yeah. So you would have to modify that file, and you could, I mean, once you did it here in the GUI, what you could do So let's say I specified that column for water solubility, and let's say it was, called my solubility. If you change that and then save it, I believe that overwrites the file that saves on the system. So then you could run it from the command line with just that input into the ST file or the SMILES file.
Yep, those are very kind of straightforward XML formatted files. Pretty easy to open up in a text editor and edit by hand as well. There's a lot of other interesting parameters in there too for more advanced users. You can, there's formulation parameters and a lot of other things that we chose not to expose in the graphical interface because they're, not really intended for our audience, which was more early discovery medchem types, not DMPK experts.
Right. Let me just show a quick example of that file. So this is the HIA file. It has the name of the ACAT file. So this is a reference to another file, molecular weight, et cetera down here. Different parameters for the dose, particle radius, density. So these can all be changed within this file. So it's very flexible and includes a lot of different fields. So here's where we're specifying the blood to plasma ratio. So there has to be a column called RBP. You could change this. You can change the body weight of the subject, the default dose, et cetera in that file.
Yeah, one of the extensions that was requested by this pharmaceutical partner that we had in the last several months when we enhanced HTPK was to allow for multiple versions of this file, this parameter file that Michael just showed. So this particular company, they do a lot of runs and like to alter a lot of parameters, and they didn't want to have to constantly make changes to the single file that we distribute with the software. So they have multiple versions of the file. And when you run now from the command line, you can specify which of those files you want to use. So that was an enhancement that's going to be added in this upcoming version of the software.
Yep, and that's just on this side. So that's the specified.
Yep. A new feature. Okay, thank you again, Michael. So we have reached our time limit here. Why don't do you have that other slide handy there with the email addresses just to leave up in case your question wasn't answered? You can feel free to email either Michael or myself or use the general info address, info@simulationsplus.com as well.
And you can also contact your distributor in your country too.
That's probably easier, yes.
Yep.
Okay, with that, we will conclude today's webinar. If you missed any part of the presentation, the playback will be available at our website, www.simulations-plus.com. Thank you again for joining us and have a wonderful day.
Bye-bye, everyone.